In this class, I am going to talk about the hybridization in triangular planar compounds. Hybridization in triangular planar compounds. Hybridization in triangular planar compounds. Okay. And let me give you an example of a triangular planar molecule, that is BF3. BF3 is a well-known example, right? So what are the symmetry elements present here in the triangular planar compound? The symmetry elements. So let me make a triangular planar compound here. So here is a triangle, okay? And in the midpoint of this triangle, we have the central atom, okay? So for example, boron will be here. Boron will be here. And we have, if it is boron, we have 3 fluorine atoms here. This one a fluorine atom, this one the next fluorine atom, this one is a last fluorine atom. Okay, and the bonds are there from boron to fluorine. So we can call this as a BF3. BF3. So this is BF3. And what are the symmetry elements present in this one? Let me call the first fluorine as a fluorine 1, this one as fluorine 2, and this one as a fluorine 3. Okay. And what are the symmetry elements present here? The symmetry elements present here, one of the symmetry elements is C3 axis. And the C3 axis is passing through this boron atom. Okay. And then it is perpendicular to the plane of the molecule itself. Means it is perpendicular to the molecular plane. So here is the boron atom, and C3 axis is passing perpendicular to the plane of the board or plane of the molecule itself, and it is passing through boron. So this is a C3 axis. Okay. So let me write C3 axis here. I have not drawn the axis here because the axis itself is perpendicular to the plane of the board. So it is not easy to draw the axis here, but you can imagine what is C3 axis here. And in addition to the C3 axis, there are C2 axis, right? C2 axis. So this is a C2 axis. For example, each boron fluorine bond is a C2 axis. So this one is a C2 axis. And this one is also, so this is a C2 axis. That is the first C2 axis. Then there is a second C2 axis like this. So this is a second C2 axis. And there is another C2 axis like this, right? So there are 3 C2 axes. So this is C2, and this is C2, and this is also C2. Okay, C2 axis 3. And then we have a sigma h plane. What is sigma h? The plane which is perpendicular to the principal axis. The principal axis here is the C3 axis, and the C3 axis is perpendicular to the plane of the board. Therefore, plane of the board itself is a horizontal plane, or molecular plane is a horizontal plane. So this triangle, the plane of this triangle is a horizontal plane. Okay. And then we have a sigma v. Sigma v. What is sigma v? It's a vertical plane, or the plane containing the principal axis. So there are 3 sigma v's, and each sigma v is containing the C2 axis, or the boron fluorine bond in this case. Okay, so here is a vertical axis, okay, and this vertical plane, and this vertical plane is perpendicular to the plane of the board, and another vertical plane is through this boron fluorine bond, and another vertical plane is through this boron fluorine bond. So there are 3 vertical planes, or 3 sigma v's. And in addition to that, there is S3. What is S3? That is the improper rotation, right? So S3 axis is actually coinciding with the C3 axis itself. So C3 axis and X3 axis are both are same axis, but the operation is different. C3 means it is a rotation by 120 degree, but S3 axis means 120 degree rotation plus a reflection perpendicular to the plane of rotation, that is S3. So even if the axis of C3 and S3 are same, the operations are different. Okay, so the S3 axis is coinciding with the C3, And these are the symmetry elements present in the boron trifluoride or any triangular planar compound like this. Okay. And now we can list the symmetry elements here. So how there is one E, that is an identity operation. E is there. Then in addition to that, there are two C3. What is meant by two C3? Two C3 means there is C3 is there, or I will list all these things here. E is there, then C3 is there, then C3 square is there. C3 square means carrying out C3 two times, right? C3 cube is also there, but it is equivalent to E, so I am not writing it. Okay. Then three C2 operations are there. So three C2 operations. And then a sigma H operation is there. Then in addition to that, there are S3 operations. What are S3 operations possible? S3 is there. Then S3 square is there. Okay. S3 cube is there. Then S3 raised to 4 is there, or S3 4 times is there. Then S3 5 times is there, and S3 6 times is there. Okay. So these are the S3 operations available. Okay. But we are not listing all the S3 here. You can see in the character table we have listed only two S3. Why is it like that? We will see that S3 square. S3 square is nothing but S3 carrying out S3 two times. So that is equal to C3 square. So this is C3 square. C3 square. So we have already written C3 square here. So we don't need to write S3 square again. Okay. What about S3 cube? S3 cube actually it is sigma H. We have already written sigma H here. So we don't need to write sigma, S3 cube again. What is S3 raised to 4? S3 raised to 4 means carrying out S3 4 times, and that is equivalent to C1. S3 raised to 4 is equivalent to C3. It is equivalent to C3 one time. Okay, it is already written there, so we don't need to write it again. Okay, and what is S3 raised to 5? That is a unique operation. But S3 raised to 6, S3 raised to 6 is nothing but E, and it is already written there. So we don't need to write all these S3 operations. This one we can omit, this one we can omit, and this one also we can omit, and this one also we can omit. Okay. So in effect, how many unique S3 operations are there? S3 is there, and S3 raised to 5 is there, and that is why we have written only two S3 here. Okay. And in addition to that, we have a 3 sigma V also. 3 sigma V. Okay. So these are the symmetry, unique symmetry operations present, or non-redundant symmetry operations present in the BF3 molecule or any triangular planar molecule of this kind. Okay. So here I have given the character table. Why the character table is given here? Because we are going to find out the hybridization, or we are going to find out the symmetry allowed hybridization patterns in this type of molecules. Okay. For that, we have to construct a total character. You already know how to construct the total character for the hybrid orbitals. I am detailing this for the last three lectures. Okay. So I am going to write three vectors corresponding to three bonds present in this type of a triangular planar molecule. Okay. So the three bonds here are, okay. So let me take this one. This one as let me take this picture to down. Okay. So that we can visualize it fast. Okay. I will put it there down. So I am going to construct the total character. So in order to construct the total character, I am giving the vectors along the bonds. Okay. So these are called the bond vectors. I have already given a lecture on the transformation of bond vectors and their symmetry properties. Okay. You are recommended to watch that lecture before proceeding. Okay, then you will understand it better. So I am going to draw the bond vectors here. Okay, this is one bond vector, this is another bond vector, and this is another bond vector, and these bond vectors are passing through the bonds. Okay, so since they are vectors, they have a directions as well, so I am giving the arrows here. Okay, arrows, and the vector starts from the middle atom, and then the vector is oriented into the three corners of this equilateral triangle. Okay, and why these bond vectors are important here? Because these bond vectors are actually oriented along the directions of the hybrid orbitals. Why this molecule has a particular geometry like a trigonal planar? It is because this central atom has a particular hybridization pattern, and in the hybridization pattern the hybrid orbitals are oriented through particular direction, because hybrid orbitals are highly directional. Okay, and these are oriented at a particular direction. That is why the bond vectors are very important here, and the directions of the bond vectors will give the directions of the hybrid orbitals itself. So any transformation of the hybrid orbitals in this type of molecules will be indicated by these vectors itself. We can see how these vectors are being transformed in this molecule during every symmetry operation. So we have different symmetry operations here. You can see how many symmetry operations are there. 1, 2 plus 2, 3, then 6, then 7, 7 plus 2, 9, 9 plus 3, 12. So the order of this group is equal to 12. Order of the group is equal to 12. Right, I have to write here. Order of the group H is equal to 12. Okay. So we are going to perform these operations, these unique operations in this molecule, and see how these bond vectors will change. Okay, if the bond vectors are retaining their position in a particular operation, it will be given the character okay, 1. Okay, so if one bond vector is retained the position, the character will be given 1. If three bond vectors are retained their position, and then it will be given the character, total character 3, like that. So corresponding to every operation we are going to carry out this one. We need to carry out one operation each in each class. Okay, so in C3 we have two operations here, C3 and C3 square. We don't need to perform C3 and C3 square together, because whatever operation you are carrying out, the character is not going to change in within a particular class. So we have to do only C3 alone here. Here we have to do only one C2. Here we have to do only one S3, and here we have to do only one sigma V. That's all, because that will say the character of the other elements in the same class. Okay, and now we can see what is the result for the total character for operation E. Okay, I am going to write the total character chi t here. And for operation E, the total character is equal to 3, because during E operation or identity operation, none of the vectors are changing their position. So all the vectors retains their position, and therefore the total character is 3. But during performing the C3 operation, or after performing the C3 operation, we can see that all the vectors have changed their position. You can call these vectors as R1, R2, and R3. Okay, these are the names of these vectors. So during the C3 operation, R1 will come in place of R2, R2 will go in place of R3, and R3 will go in place of R1 if it is a clockwise rotation. So all the vectors have changed their position. Therefore, for C3, the character is 0. And what about the character for C2? C2. C2 is the rotation about this axis, right? And each C2 axis contains one bond, one BF bond in this particular case. Or we can say each C2 axis contains a vector, right? So since each C2 axis is containing a vector, that vector alone will retain the position, but the other two vectors will change their position. For example, if you are performing the C2 operation through the R1 vector, okay, then R1 will retain its position, but R3 and R2 will exchange their position. So what is the total character corresponding to the C2 operation? The number of vectors retaining the position, that is equal to 1. Okay. And what about sigma h? Sigma h is a horizontal plane, that is a molecular plane itself. So even if you are performing an of reflection about the molecular plane, none of the vectors are going to change their position because all the vectors are lying in the molecular plane itself. Therefore, corresponding to sigma h, the total character is equal to 3. Okay. And what about S3? Corresponding to S3. S3 is an operation which is in which C3 is performed first. And when a C3 is performed, then it's all the vectors will change their position. Then that is C3 is followed by a reflection also. So during this operation, all the vectors will change their position. Therefore, the total character is equal to 0. And what about sigma v? Sigma v is a vertical plane, and this vertical plane will contain the C2 axis, and C2 axis is passing through one of the BF bond, and therefore three C2 axes are like that. Corresponding to three C2 axes, there will be three sigma v's also. So in the sigma v, in each sigma v, there will be one bond vector. Therefore, that vector is not going to change the position. Other two vectors will be changing their position. Therefore, during the sigma v, the total character is equal to 1. So, this is our set of total characters. Okay. And then now, with this total character 301, 301, 301, 301. Okay, we can now calculate the number of times each irreducible representation will appear in a reducible representation corresponding to this total character. Okay, did you understand what I said? There will be a reducible representation corresponding to this total character, and that reducible representations can be reduced further to irreducible representations. So which are the irreducible representations in this character table are contributing towards it? Okay, that we can find out using the reduction formula. We have explained this in detail in our previous lecture, so I recommend you to go back to the reduction formula or my lecture on reduction formula and watch it very well. Okay, so here I am going to calculate the number of times the A1 prime will appear. Number of times A1 prime will appear. Before that, I will give you once again the reduction formula here. The reduction formula says that Ni is equal to 1 divided by H into sigma gr chi ir chi r. Okay, you already know this reduction formula. The terms are Ni is the number of times an ith representation will appear in a reducible representation corresponding to a total character set. Okay, the Ni is the number of times the ith representation will appear, and H is the order of the group. In our case, order is equal to 12. Okay, we have already calculated the order as 12. Okay, and then we have GR. GR is the number of elements in a class represented by the operation R. For example, if you are looking at the operation C3, and C3 belongs to a particular class, right? And in that class, there are two elements. That is why it is written 2C3. So GR in that case is equal to 2. Okay. Like that, if you are going for sigma V, then there are 3 sigma V's. So GR in that case is equal to 3. So corresponding to each operation, there will be a corresponding GR value. That GR value is the number of elements in the class represented by the operation R. Okay, and chi ir is the character of the character corresponding to the operation R in the ith irreducible representation. For example, if you are calculating for A1 prime, the first irreducible representation, okay, then I is nothing but the A1 prime. A1 prime is the irreducible representation we are considering. At that case, if you are looking at the C3 operation, the character chi I is 1. If you are looking at the S3, the character is again 1. Okay, so chi ir is the character corresponding to the operation R in the ith irreducible representation or the irreducible representation under consideration. And what is chi r? Then chi r is the character corresponding to the total character or character corresponding to R in the total character set. For example, if you are taking C3, okay, in corresponding to C3, the total character set is in total character set, we can see the number 0. Therefore, chi r in the case of C3 is equal to 0. But chi r in the case of sigma h is equal to 3 because we can see this number here. Okay, so now I have explained all the terms involved in this reduction formula, and using this reduction formula I am going to find out the number of times each irreducible representation will appear in the total character set. Okay, so before proceeding, let me pick which are the irreducible representations I am going to use for calculation. I don't need to calculate all the irreducible representations, calculate for all the irreducible representation, because I can know in advance that some of the values that I am going to get from here will be 0. Okay, that I can know by looking at the third and fourth area of the character table. You can see that in the first line of the character table, or in the first row of the character table, that is corresponding to A1 prime. You can see that z square is there, z square, right? That corresponds to dz square orbital. So that character, that irreducible representation we should consider, okay? Because that irreducible representation has something corresponding to an atomic orbital. So this irreducible representation we will use for calculation. What about the next one, A2 prime? The corresponding to that, there is no atomic orbital given in the character table. Okay, so since there is no atomic orbital corresponding to this one, we don't need to calculate this. The answer is obviously 0. Even if we are calculating, answer obviously will be 0. But we have to calculate for the E dash, because that corresponds to the px and py orbitals here, and it corresponds to dx square minus y square and dxy. So that is an important character set. Okay, and what about A1 double prime? We don't need to calculate for A1 double prime because there is no orbitals corresponding to this. But we have to calculate for A2 double prime because there is an orbital corresponding to A2 double prime, that is a pz orbital. And then we have to calculate for E double prime because there are orbitals, d orbitals corresponding to that, dxz and dyz. So we can neglect A2 dash and A1 double dash, or A2 prime and A1 double prime for the calculation, because those values are going to be 0 obviously. Okay, now let me calculate it for A1 prime. So n A1 prime, n A1 prime, so n A1 prime is equal to, from our equation, 1 divided by 12 into what is A1 prime? That is this one, 1 1 1 1 1. All the characters are 1 in A1 prime. So we have to write like okay, g r into chi r into chi r. So in the case of E, g is equal to 1. So let me copy this down so that I can do it fast. Okay. So this is the representation. Okay. Let me copy this and put it down. Put it down here. Okay. So let me, if I put it here, the reduction formula will not appear there. So, okay, anyway, I'll put it here. The calculation I will do a little bit down. Okay, sorry. So A1 prime is equal to n A1 prime is equal to n A1 prime. N A1 prime is equal to n A1 prime is equal to 1 divided by 12 into gr into chi r into chi r. In our case, it is, in the case of E, it is 1 into 3. So that is equal to 3 plus gr into chi r into chi r. In the case of C3, that is equal to 2 into 0 into 1, that is equal to 0. So this is 0 plus then gr is equal to 3. In the case of C2 it is 3. 3 into 1, that is equal to 3 plus, in the case of sigma h, it is 1. So 1 into 3, that is equal to 3 plus In the case of S3, it is 2 into 0, that is equal to 0, plus then 3 into 1 into 1, that is equal to 3. Okay, so this is equal to 3, 3, 3, 3. Okay, 12 by 12, that is equal to 12 divided by 12, that is equal to 1. So A1 dash will appear one time. And now I am going to calculate for next is E dash, right? We can look here. Next is E dash. So when I am doing the calculation for E dash in the same way, let me put this one E dash here. Okay, the characters corresponding to E dash, I will put it here. Then I can calculate fast. So this is corresponding to E dash. So now I am going to calculate the N E dash, and the N E dash is equal to 1 divided by 12 into, okay, now I need to just multiply these numbers with the numbers appearing here, okay, because these numbers are already multiplied with 1, okay. So chi r in this case is equal to 1. So we can replace this 1 with other chi-ars from this E dash representation. So I can do it very fast. So you will see this. Okay. So 3 into 2, that is equal to 6, plus then 0 plus 0 plus then 2 into 3 into 2, that is equal to 6, plus 0, okay, plus 0. Okay, that is 6 plus 6, 12. 12 divided by 12, that is equal to 1. That is equal to 1. And now I am going to calculate for next one, A2 double dash, this one. Okay, A2 double dash. So let me take the A2 double dash from here. A2 double dash. And put it down, and I calculate for A2 double dash. So in the A2 double dash, we have 1, 1, minus 1, minus 1, minus 1, minus 1, minus 1, then last one is 1. Okay, so let me calculate for A2 double dash. So N A2 double dash is equal to N A2 double dash or double prime is equal to 1 divided by 12 into, okay, 3 plus 0 plus and then minus 3 plus minus 3 plus 0 plus 3. Okay, that is equal to 3 minus 3 minus 3 plus 3, that is equal to 0. Okay, that is equal to 0. Now I am going to calculate for the last one, that is E double dash. Okay, this one, E double dash. So let me put this E double dash down there. Okay, and I will calculate for E double dash also. So for E double dash, I can calculate like this. So N E double dash, then E double dash is equal to 1 divided by 12 into 6 plus 0 plus 0 plus minus 6 plus 0 plus 0. Okay, that is equal to 6 minus 6 divided by 12, that is equal to 0. Okay, so we have calculated everything. And now we can see that we have N okay, this one, yeah, we have N A1 dash is equal to 1. Okay, this is equal to 1, and we have N E dash is also equal to 1. Okay, all other irreducible representations give the value 0. Okay, it means that the total character can be represented like, or chi t is equal to N A1 dash, that is 1 A1 dash, A1 dash, right? The first one is A1 dash, A1 dash, A1 dash plus then E2 A1 dash plus E dash, right? The second one what we calculated, E dash, this one. So A1 dash plus 1 E dash plus E dash. Okay, so this is what we can write. And now what are the atomic orbitals corresponding to A1 dash and E dash? That we can get from the character table. So corresponding to A1 dash, we have dz square. Dz square is the orbital corresponding to A1 dash. In addition to that, we have s orbital also, because s orbital is totally symmetric. It is, even if it is not written in the character table, it is obvious that s orbital is totally symmetric, because A1 dash is a totally symmetric irreducible representation. All characters here are 1. Therefore, s orbital is obviously is a totally symmetric orbital. Therefore, we don't, even if it is not written in the character table, we have to assume that s is already there. Okay, so we have s and dz square from this part. Let me write it there, s and dz square. So A1 dash, A1 dash. So let me take another color so it will not be easier for your eyes. So A1 dash, A1 dash is S and dz square. These are the two possibilities from A1 dash. So one A1 dash plus E. Okay, what are the atomic orbitals corresponding to E dash? Okay, E dash is equal to this one. Okay, Px Py, then dx square minus y square dxy. Okay, dx Py, dx square minus y square dxy. So let me write E dash is Px, Px, Py. These are degenerate set because it is written inside the bracket, right? Px, Py. These are degenerate set. Okay, these ones. Then we have another degenerate set, that is dx square minus y square and dxy. That also we have to write. Ds square minus y square, dx square minus y square, then dxy. Okay, these are also degenerate set. It means that they transform together. Px and Py transforms together, and these two d orbitals also transforms together. Okay, these are the orbitals available there for the hybridization. Okay, orbitals available for hybridization. And now we have to check the validity of this one, because chi t is equal to a1 dash plus e dash. So the sum of the dimensions, this is one dimensional representation, this is two dimensional representation. Therefore, the sum of the dimensions is equal to 1 plus 2, that is equal to 3. So this should be equal to the number of hybrid orbitals that you are expecting. The number of hybrid orbitals that you are expecting is 3, because we are considering a trigonal planar molecule. So this calculation is correct. You have to check always the validity of the calculation by summing up the dimensions. Okay, so that sum of the dimensions should be equal to the number of hybrid orbitals. Okay, now these are the possibilities. We have 1a1 chi t is equal to 1a1 dash plus 1e dash. Means at a time we have one of the choices from a1 dash and one of the choices from e dash. Okay, so it can be s from here and px and py from here, and then s from here and dx square minus y square and dxy here. Okay, so these are the two possibilities between x and px py, and then between x and dx square minus y square. Okay, and then if it is dz square, then the dz square can be with px and py, and dz square can be with dx square minus y square dxy also. So how many possibilities are there? 4 combinations are possible. Okay, the 4 combinations possible are, for the first combination possible, that is s plus, okay, px plus py. This is one combination. The second combination is s plus dx square minus y square, plus dxy. Okay, third combination possible is dz square. Instead of s we have dz square, plus px plus py. Okay, this is another combination. And the last combination is, the fourth combination is dz square plus dx square minus y square plus dxy. Okay, these are the four combinations allowed by symmetry. Four combinations allowed by symmetry. Maybe we can call this as the Sp2 hybridization. One s and two p orbitals, Sp2 hybridization. Maybe you can call this as d2s hybridization. Okay, you can call this as uh, uh, P2D hybridization, P2D hybridization, or you can call this one as D3 hybridization. Okay, all these hybridizations are possible by symmetry. But I always say this is not the final answer to a hybridization shown by a molecule. This group theoretical process or this group theoretical method only gives you the hybrid orbital combinations or possibilities for the hybrid orbitals allowed by symmetry. But symmetry is not the only one factor which determines the hybridization. There are other factors like orbital availability, then energy of the orbitals, etc. For example, energy of the orbital will be determined by quantum mechanics, and the orbital availability will be determined by the atom itself. Okay, so different atoms may have different electronic configurations because they have different atomic numbers and so on, and they have different oxidation states and so on, like that. So orbital availability will be different. It may be depend upon the atom or the ionic or oxidation state, and energy depends upon the quantum mechanics. So for example, quantum mechanics gives you the energy, and that those are also the criteria which will lead to the determination of the hybridization. And the third criteria is symmetry, and the group theory will give you the answer from that criteria only, whether it is symmetrically allowed or not. That's all. If it is symmetrically allowed, which are the orbitals taking part in the hybridization? That is what the group theory can tell us. Okay, so if you are taking the BF3 as the example, okay, boron trifluoride as the example, then what will be the case in the case boron trifluoride, the example that we considered in the beginning itself? So in the case of BF3, we have boron as the central atom. Okay, boron has the atomic number 5. Okay, so the configuration is 1s2, 2s2, 2p1. Okay, 2p1. So it has 3 electrons in its valence shell. 3 electrons in its valence shell. So it belongs to boron, aluminum, gallium. All these belong to the third group, right? Third group means if you are considering only the main groups, then it is in the third group. Okay. Otherwise, it is the 13th group. Okay. So here we have the valence shell configuration like a 2s2, 2p1. So if I am drawing like a box, okay, this is a 2s orbital, and these are the 2p orbitals. 2p orbitals are there 3. So in 2s we have 2 electrons, and 2p orbitals we have 1 electron. This is 2p. Okay. And for the hybridization, what happens is that boron goes to the excited state. Boron excited state. Okay. In the excited state, one of the 2s electrons will be jumped to the 2p orbital. So the configuration will be 2s1 and then 2p2. Okay, it will be like this: 2s1 and 2p2. And now these s and one of the s orbitals and these 2p orbitals, which are half filled, they will undergo hybridization. Okay, so the hybridization will be like this. Sorry, hybridization will be like this. So they undergo hybridization. So when they are undergoing hybridization, we can call this as the Sp2 hybridization. Sp2 hybridization. Hybridization involving one s orbital and two p orbitals. So what are the s and what are the p orbitals here? Allowed by symmetry. The group theory says that it is a s orbital plus px plus py. It is not pz. You have to keep it that you have to note that it is not pz. It is px and py. So this one is s, this is s, and this is px, and this is py. Okay, pz is not taking part in the hybridization. Okay, that is very important. And you can see that s orbital is a spherically symmetric orbital, but px and py, they are in the xy plane, right? So the hybridization, it happens in the xy plane, and you have to remember that our C3 axis was in the z axis. Okay, C3 axis was in the z axis. Okay, and therefore, hybrid orbitals will appear perpendicular to the C3 axis. Means the hybrid orbitals will be in the xy plane. Okay, that is a plane perpendicular to the C3 axis, or it is the molecular plane itself. Okay, this is what the group theory can tell us. So the 2s orbital, 2px orbital, and 2py orbital of the boron will combine to give hybrid orbitals, sp2 hybrid orbitals. You will get 3 sp2 hybrid orbitals, and these hybrid orbitals are highly directional, and they will be oriented from the central atom to the three corners of an equilateral triangle. Okay, and these hybrid orbitals are carrying a single electron. Each hybrid orbital is having a single electron, and this electron will be paired with the electron coming from the fluorine atom, so that a covalent bond will be formed. Okay, this is what we can understand from here, and this simply explained the sp2 hybridization. This is what we explained now, and that is true for the main group elements. Okay, but that is not always true for the transition metals, because in the case of transition metals, d orbitals may also have some contributions. Okay, so the other hybridization possibilities, even though it is rare, maybe they may be playing in the case of the d or the transition metals. Okay, okay, that is what we have to understand, and this is what group theory says. Symmetrically, it is possible if the energy and the other factors are okay. Then obviously this type of hybridizations may also be possible. Okay, and this is what group theory can tell us. So I hope you understood the entire lecture. Here in this lecture, we were talking about the hybridization in trigonal planar compounds, or the compounds belonging to the D3H symmetry. Okay, D3H symmetry. And I hope you understood the procedure. We constructed the total character, and then we reduced the total character to differently reduced representations by applying the reduction formula. And we found that the total character is composed of one A1 dash and an E dash. And then we found that the prominent possibility in this case is a sp2 hybridization, and we cannot neglect the contributions from the d orbitals if we are considering the transition metals also. That's what I wanted to tell you about the hybridization in trigonal planar molecule in terms of group theory. I hope you enjoyed this lecture. If you have any doubts, please don't hesitate to ask me. Thank you for watching, and stay tuned.